Okay. I have the honor to represent here near Shavit. He's currently have three affiliations at Tel Aviv University first, MIT, and a startup called Neural Magic. And he's going to teach us how to use tissue instead of silicon. Then
Thank you very much. So, so my talk today, this is not the original title. I decided that I was going to kind of do a bit of a rant about a thing that is, yeah, like this? Wow, okay. I'm going to do a bit of a rant about a thing that's on my mind, which is the direction in which our hardware and software for machine learning is going. And so, but I want to start maybe at the very beginning and kind of lead up to the main point. So I want to tell you a little bit about you know, what I do for research. So what you're seeing here is a picture. I think most of you can identify what this is. We know that you can do it in about 1/100th of a second. Okay, this is Mount Fuji, right? And in that amount of time, a very small number of neurons can actually fire on the order of 2 or 3 or 4, okay, in sequence. Okay, and yet, you know, there is a great. Okay. So there's a bit of a delay. Okay. So, right, you do this with your mind, neural tissue. Okay? And you know, and I actually do research. This is, where do I aim this? Is the question. Oh, there we go. Right? I actually do research in computational neurobiology in a field called connectomics, which I want to tell you a little bit about. Okay? So in connectomics, we study, you know, how neural tissue works. So what you have here is a picture of a neuron, right? Our brain is actually built out of tens of millions, in fact, close to 80 billion neurons, okay? And each neuron has kind of an entry point called a dendrite, an output point called an axon, and a kind of a cable that goes between them. The axon kind of delivers information. And the way this is done is with synapses that connect neurons together, you know, in the dendrites, and connect neurons together in the axons. And what typically happens is that, you know, an electric signal is collected in the dendrites and then passed on when it passes a threshold down the axon and fires into the subsequent neurons. So this kind of process is what actually runs the computation in our brains. Now, sorry about this. I have to learn how to do it. In connectomics, we try to map, okay, this connectivity, this tissue. We take a small sliver, okay, of, let me try to show it. So we take a small sliver, okay, of an animal brain. In this case, this is, you know, a picture of something, how we do a mouse, for example. And you slice it and dice it. You take like a cubic millimeter and you slice it 30,000 times into these thin layers, okay? Put it on tape, so you have this brain on tape, and then we take and put it under an electron microscope. This is my colleague Jeff Lichtman from Harvard next to the multisim microscope. It's kind of to show you how small Jeff is. And then what we get from that are, you know, essentially these wafers that we feed into the microscope. And from the microscope, each tiny little piece of brain like this, okay, is actually imaged at a very high resolution with the electron microscope. And if we take all these slices, together, yeah, if we take like, you know, 100 terabyte worth of slices together, then what we get, you know, is this little kind of cube, right? And we can try to reconstruct what's in this cube, okay? And, you know, this little cube that is 100 terabytes, okay? If you look at it, this is its size. So it's like a grain of salt. If this is a penny, that's the size of this little cube, right? And we try to look inside this cube, right, with essentially machine learning technologies in order to actually image what's in there and reconstruct the connectivity, okay? So what you're seeing here is what we call a saturated reconstruction, okay? That's what we're trying to do, just to actually get all the connections that are in there, okay, in this tissue. And I want to show you an example. Oh, I hope I did it right, yeah. So here's an example of a little sliver of mouse brain. And what you see are two dendrites, a green one, a tiny little branch of a dendrite. And in this tiny little branch, okay, you know, if you look at, for example, at this little connection, which is going to be a synapse, okay, here are all the dendrites that are around those two dendrites, okay? So it's really dense, okay? And here are all the axons in this volume. And here are all the glia cells in this volume, okay? And all this, when you combine it together, okay, will be, you know, this little tiny piece of brain, okay? And it is, you know, about 100,000th of that little tiny piece of, you know, of that grain of salt, okay? This thing here. Now, it looks like it's immensely dense, right? And computes an enormous amount of computation. And this is what I want to talk to you about, okay? Because actually, when we actually look at this, okay, it turns out the amount of computation is very far from what we're imagining in our minds, okay? So I just want to share with you one more image, okay, before we go on, and I'm going to use this image later on in my conversation with you. And what you see here is a dendrite in green and an axon in blue. And you can see that this axon is connecting to the dendrite in about 5 different places, okay? And these 5 connections, you can imagine this axon is very long. And in this little sliver of a place, it connected already in 5 different places with this dendrite. Cool. So what did I do? So now, having seen this, I want to take this knowledge that I've accumulated a little bit, doing a lot of computational neurobiology, and talk about machine learning, okay? I'm actually originally a multi-core processing guy. I've been doing 30 years of multi-core software, okay? And when we think of machine learning, right, the first thought that we have in our minds, right, is that, you know, if we're going to build a machine learning device, okay, we need to make it neuromorphic, okay? It's got to look like the brain. It's got to have this parallelism like the brain. And we are building such systems, right? We're building systems, right, that are capable of delivering this massive compute that the brain does. You know, you have GPUs and TPUs, and Intel just came out with their NNPs, right? And there are about 70 different startups. Now I hear there's even 100 different startups, and they're all building hardware for machine learning. Okay? And the idea is we got to build this hardware because there's so much compute, and we got to supply the compute so that we can do what the brain does. Okay? Good. So what are we building? You know, we're building these devices like GPUs with 5,000 cores that run on about 16 gigs or 32 gigs of memory, high bandwidth memory, right? And you know, so you run your machine learning, you put your models and data into this kind of memory, and then you run trying to generate, you know, hundreds of teraops per second, apply it to the, you know, to this model and have it compute something. Right? And then if you want to really compute on a massive scale, right, then what you do is, this is the image, you know, this is the idea of what, you know, brain scale computation is according to Google. Well, even less than brain scale, right? It's essentially, we're going to take these devices, we're going to connect them together in these giant pods, right? And then we're going to run that, and we're going to get hundreds of petaflops of compute. Hundreds of petaflops of compute. Sorry, I'm told that I have to, right? So this is the idea. Okay? So I want to kind of think with you a little bit about this idea. Okay? So what is the computation in our brain? And this is where the tissue versus silicon comes in, okay? So, you know, the human cortex is about 16 billion neurons, okay? Give or take. And a cortical neuron spikes about every 0.16 times per second, okay? And there are about 7,000 synapses per neuron in the cortex, okay? Now, how many connections does it make with other neurons over these 7,000 synapses? I showed you in a tiny sliver it connects with another neuron 5 times. Probably the number of actual other neurons that it connects with, somewhere in the order of 700, probably even 70. Okay, we still don't know. This is part of the research that we're doing, trying to understand exactly what that connectivity is. But I'm just going to use the number 700. And so with that number, if you try to compute what the computation is that is going on in cortex, okay, it amounts to about 2 trillion operations per second. Okay, 2 trillion operations per second, right, if you think about that, is like an iPhone. Okay? So there's an iPhone of compute going on in your head. Okay? Right? So the cortex, right, is 5 to 6 orders of magnitude less compute than the TPU pod. Think of a task that we all kind of know and love in deep learning, right? Image recognition. So, you know, you take a 224 by 224, image, right? About 0.05 million pixels, right? It takes about 20 to 30 billion operations for us to run it with ResNet 50 or one of those networks, right? And the human iris, okay, when it takes in an image, right, does about 100 million pixels. So that's about 2,000 times more than the 224 by 224 image that we work with typically, right? Now, you know, a neural network to process this amount of pixels, right, with one of the networks that we know, would take about 40 trillion operations. Okay? So if you think about that, right, if we recognize an image in 13 milliseconds, right, which is kind of the time that it takes you to like recognize Mount Fuji, right, then even if we use the whole cortex, right, then what you have here is about 20 billion operations per image, okay? So this is about 3 or 4 orders of magnitude, right, more efficient than what you have, right? We recognize it with our brain images 3 or 4 orders of magnitude more efficiently than we do right now with neural networks running on today's hardware, okay? Good, so that has to do with compute. And now, let's talk about memory size. So, if you think about our brain, about 300 trillion synapses. So if I want to represent these synapses as a graph, right, then, you know, this graph should be about a petabyte of memory, okay? A simple representation of this graph is about a petabyte of memory, okay? And, you know, a GPU typically has about 16 to 32 gigs of high bandwidth memory. I connect 5,000 cores to this memory. It's hard to scale. That's what I have, 16, maybe 32 gigs, okay? And so, you know, this is compared to, you know, you can buy a desktop now with 1.4 terabytes of memory, right? A CPU has endless memory compared to these devices, okay? And so if we think about this, right, when I think about the GPU or TPU pod, right, it has 4 or 5 orders of magnitude too little memory, okay, compared to what we want. So you know, it has a lot of compute and very little memory. So small models, and we apply to them a lot of computation. So if you think about the brain in silicon as we think about it right now, what our image of what, you know, machine learning computation is like, we think about it, you know, I want to generate a petaflop of compute and apply it to a cell phone worth of memory, right? But what we really need, what our brain is, okay, is a petabyte of memory with a cell phone worth of compute, right? This is where we need to go, and this is where we are. And probably the truth is not at either end, but it's somewhere in the middle, okay? And so right now, the hardware that we're building is not the right hardware for the goal that we want. And why is this? Why aren't we building the right thing? Well, we're not building the right thing because we don't know what the graph is. We don't really know the algorithm. And what is typical in computer science when we don't know the algorithm is we apply a lot of compute to it. Okay, so this is the stage that we are in. But we're learning, okay? We're not, sitting and resting. The algorithms are evolving, okay? In May, the Google guys came out with efficient nets, right? I don't know how many of you have heard of efficient nets, but if this is the graph of, of the number of parameters versus the, accuracy, right? Then you can see that efficient nets, right, are kind of the top of the curve. If you look, at efficient net B0, which is the smallest efficient net that is described in this paper, right? Its size is the size of a network that we call MobileNet, and its accuracy is the accuracy of ResNet 50. Okay, so we can get the same accuracy of a much larger model, right? A much higher compute model with a much smaller one. And efficient at B4, right, is the size of ResNet 50 in terms of the amount of computation, right? But the accuracy is the same that we get with these monster networks like AmoebaNet. Okay, my point is we are learning what the algorithms should be. Okay, and this is an evolutionary process that is going to go on, and with time we're going to learn how to do things with less compute and more memory. Because if we are mimicking the computation in our brain, that's where we're going. Okay? Not to more compute and less memory. So I just want to show you for those two networks, you can actually, run these networks very efficiently. This is what my company, Neural Magic, does. So with Neural Magic software, here's an example of running efficient at B0. Okay? So this is on Amazon Web Services. The same compute that batch size 1 inference, a Volta GPU that costs $3, you do the same thing, okay, with a 4-core CPU that costs $0.34. It's exactly the same performance, okay? Same network, same accuracy, everything. If you want to think about throughput, batch 64, where this is what the GPUs are good at. Batch it all together, fill the pipeline, deliver performance. So, a 24-core CPU, okay, delivers better performance than a Volta, okay? And you can actually, on Amazon, you can just, instead of taking one, you can take 9 4-core instances, save more money, deliver twice the performance. And this is just the beginning, okay? Because the algorithms are going to get better. If you think of efficient at B0, which is a much larger network, the accuracy is the same as AmoebaNet, okay? You can deliver, Volta performance on a 24-core CPU in real time, and you can deliver, better performance with a 9 4-core instances and comparable performance with a 24-core. And this will get better. It's just, all I want to kind of show you is we're ballparking these devices with so much compute. And that's happening because a lot of what's actually going on here has to do with moving data and memory, okay? And not with the amount of flops that we apply to the problem. And remember, these CPUs that are delivering this performance are doing this without a memory limitation. Okay, this is not 16 or 32 gigs. You can do really big things. So, I'm sorry, I wanted to show one more of them. This is ResNet 50, sparsified, okay, 1% accuracy loss. Again, a 24-core CPU is about double the performance of a Volta, okay? You can, even in batch 64, you can deliver, kind of on a bunch of 4 cores, twice the performance of a Volta at the same price. Okay, without a memory limitation. So that's key to what I'm trying to say. So when I want to talk about the future of hardware, okay, so really the way I see things is this, the first mistake that we've been making, okay, is in our minds we've bought the Kool-Aid on the idea that our silicon has to mimic our brains. Okay? Why do we need massive parallelism, guys? I mean, our brain, right, uses massive parallelism because if I want to deliver 1 billion instructions per second, and what I have are these really slow neurons, right, then the only way that I can do that is by having 1 billion neurons fire together, right? So, okay, we need parallelism. But flops are flops are flops, right? If I have a sequential way to do this, for example, any modern processor will deliver 10 billion, right, flops, instructions per second, right? So I don't need parallelism for that. So the other thing is that neural tissue, okay, has the advantage of locality of reference. And this is a key thing, right? The thing that makes it unique is when my neuron fires, it fires into the neurons that do the continuation of the computation, into the next one, the next one, the next one. It's all local, okay? And so how, can we actually mimic this thing, right? Can we do this in hardware, okay? And so the way I think about it, right, is that tomorrow, okay, we can either have memory that has hardware close by to it, and there are a bunch of companies, both in Israel and in the world, that are building such hardware where what I have is a memory with very intelligent compute next to it, okay? It's not about the billions and trillions of petaflops that need to be applied, but small compute to a lot of memory, okay? Or maybe we can build, a CPU that has a better prefetching algorithm. Right now, our CPUs are prefetching, based on the idea that everything is an array. So if I fetch something, then I prefetch the next block and the next block. But if I prefetched in a graph-oriented way, maybe I could actually deliver, the kind of performance that we need with locality of reference, like our brains. So that's in the future. And today, well, on the way there, I really think that CPUs are enough. All the disadvantages, there are many disadvantages to doing things with accelerators, okay? And we have to have a really good reason not to do this with CPUs, okay? And I, for one, at this point in time, fail to see what they are, okay? And with that, I kind of want to finish and open it up for questions.
So we talk about the process, but what about the accuracy of the process? Because the accuracy, because if he's talking about the processor that you want to have, the accuracy is a important factor. Yeah, so if you want to improve the processors, to have better accuracy, so you need to more invent of this CPU.
So I'm sorry, you're saying that, let me try to understand, you're saying that accuracy requires more compute?
Yeah, yes, the accuracy of the compute.
The accuracy of...
Yeah, if we need to improve the accuracy of the compute, so we cannot use the CPU as is today.
I disagree with that, and my point being the reason, and again, this is not, I'm not saying, I'm just disagreeing it. So as a scientist, I look to the brain, okay, which is a very, very low compute device with, sufficient accuracy, right? Sufficient to do the tasks that we call machine. I'm not saying that I can do, NP-complete scheduling with this, right? I'm trying to mimic what we do, which is essentially, the same accent. I'm saying that for what we do, what my field of study of, the brain kind of says to me, well, maybe we don't need that. What we're at is a place where we just don't know the algorithm yet.
When you compare GPU to 24 CPUs,
it's not 24 CPUs. It's 24 cores on a single.
24 cores.
Yes.
There is a power change in the.
The Volta is like a 300-watt device. The 24-core CPU, I think, is 170 or 200. I'm not 100% sure, but it's somewhere there. It's less than a Volta. Yeah.
Yes. Is there any evidence that the brain is actually really similar to shallow similarity between
So,
artificial neural
so
networks?
thank you. So do I really care is the question I want to ask. In the end, what the brain is doing is some approximation function. Do I care to do it the same way with the same algorithm that the brain does it? Probably not, right? My point is not about what the algorithm is, but what the amount of computation that's going into this
But
algorithm.
that's my question. So you're assuming that the brain is doing some regression, some approximation to a function that using data that is out there.
Or something else, which costs a certain amount of compute, and I'll say that if I knew what that was, then because I know that I can just, the CPU is a Turing machine, I can just implement that, is all I'm saying here, right? And, yeah, that's all. Yes?
It wasn't clear to me the data you show comparing different models running, doing inference on CPUs versus GPUs with different batch sizes. Are these like vanilla, just take the model and run them, or are you optimizing them? I know it says MX and GPU.
No, these are just, so this is different from efficient. Efficient is just efficient, it's a Google model. You take the Onyx file, right, and you run it, right? And here, right, with ResNet, we've done a process of pruning, right? So you prune it and you lose accuracy while pruning it. So you're reducing the amount of compute. You're not changing what the core, you're not changing the structure of the network. I'm not doing structured pruning. I'm not taking out layers or I'm just pruning it based on showing it, just pruning, reducing the number of parameters and so on and so forth.
And there's like other techniques like pruning, quantization.
Sure. So this can work with quantization also. It's just, I'm not showing quantized. Sure. Yes.
Thank you. So sparsified networks take, as you said, the current structure, and then they cut out layers or connections. Do you think we need to build a different model of deep learning, or something that its base is different than our current deep learning or artificial neural networks?
So I think that we need to change the networks that we're designing based on two things. Right now, most of the networks that we're designing, okay, look like the things that run well on a GPU, okay, because that's what we're training them on, right? If I were to design a network from scratch to run on a CPU, it wouldn't look like the networks we have right now, right? So cache sizes, all these things matter. Now, in terms of the actual algorithmic to get the result, I think that what you saw with Google's, the Google networks are essentially the result of doing kind of a search through the space of networks with some limitations to find something. And I'm sure we'll get better and better at this.
But it's still within the current construction of neural networks, which is you have neurons.
Yeah, absolutely. And we can go away from that too, but I'm not in that business of understanding how to do that. I agree. We could completely leave that. Also, stochastic gradient descent could go away. And not only could it go away, I guarantee you it'll go away. So it's like, yes, sure. Sure. Yes.
You need to run first the full complex network and then to prune it, or can you create from scratch the pruned network?
So let's take that offline. There's a whole bunch of new research about that. It's a beautiful new area of research on to what extent you can actually prune a network while training it. Okay, and there's a whole bunch of results that will appear now, I think, in NeurIPS, and people are working on this problem, and there's beautiful new advances in this direction. But all I showed here were inference numbers, not training numbers. Yeah.
What are the applications
In what sense? So, again, with training, the thing that is a kind of a bottleneck has to do with, how much compute I really need to apply, right? And there is also an issue of reading and writing from memory. It's just that it has the same problem that exists with inference becomes more of a problem because I'm reading and writing parameters to memory in the current way that we do things, right? And so you need to be smarter about how you move things in and out, and you probably need to be more sophisticated if you're going to do it based on pruning, right? And then you need to be more sophisticated about how you actually run the process. Yeah. Yes. Yeah. Sure.
What do you think about all the new inference accelerators coming up? AWS announced this franchise coming. There's other companies coming in ready to develop like silicon.
I think there are advantages and disadvantages to this. So the advantages that you probably can save space in the data center, and you can probably, over time, if people use a specific accelerator, you get a better price point. I think. I'm not sure. The disadvantage for data centers, right, is that you really do have to provision that, right? And you can't use the tonnage of CPUs that are sitting around probably while you're doing machine learning on the accelerator, okay? So there's a disadvantage in that. To the software pipeline, I think accelerators are a real problem. And the reason is because they're changing how software is being distributed. I mean, if Adobe wants to sell now software that's downloadable, you have to ask the client to have a GPU. Sounds hard, right? So I think containerized virtualized software would be better served on CPUs. And in fact, most inference does happen on CPUs right now. It's just that we're building a generation of accelerators, and I'm kind of wondering how many of those will actually benefit us in the long term. Okay? Yeah. Sure. Thank you.